All right, let's go ahead and get started. It's always hard. A new chapter always feels like a lot. So just kind of gear up emotionally for it. Okay, so a couple concept things about buffers, and then we'll do lots of sample calculations. Probably not a ton that I'm gonna expect you guys to do just because it's new. So we'll do most of the calculations together, and then we'll have a couple practice ones at the beginning of class on Wednesday, okay? So a buffer is where you have an acid, a weak acid specifically, and its conjugate base. And what the benefit of this is that, just like it sounds, it buffers the pH of any given solution, meaning it keeps it relatively constant when an acid, like a strong acid or a strong base, is added to the solution. Okay, so we're gonna start, these next 3 slides, I'm gonna go back and forth between them. And this one I'm going to tweak just a little bit. So we're not actually going to talk about it in terms of Le Chatelier's, and we're going to adjust this equation, okay? So we're going to say that we have this acid and this conjugate base. So when we talk about weak acids, we're going to think about this as HA, and the conjugate base is A minus, just so we keep it in a generic form so it's applicable to any weak acid and conjugate base, okay? So if we have these two in a buffer, this is actually the buffer that our blood uses to keep the pH of our blood constant. So if we have these two species, when we add an acid or a base to it, it's going to react with one of these. So let's start by talking about adding an acid. So when we write the acid, like a strong acid, we're going to write it as H+. This could be HCl, it could be HNO3. We don't really care where it's coming from. It's just some acid that's being added to this buffer solution. So we know that when things react, they always react an acid with a base. So this H+ is going to react with the conjugate base here, HCO3 minus, okay? And what will happen is those will react, acid and base, and produce the original weak acid, okay? So we started with both H2CO3 and HCO3 in the solution. We added some strong acid, and instead of that strong acid affecting the pH, it actually just reacted with the weak base or the conjugate base to form more of that original weak acid. So the strong acid here reacts with the conjugate base instead of affecting the pH. And this is the whole idea of a buffer, is you're trying to use up that strong acid or strong base that shows up in the solution so that it won't mess the pH up too much. Okay? When a base gets added, it will react with the weak acid. So to represent the strong base, we're just going to do OH minus. It's going to react with the weak acid, H2CO3, and form the conjugate base, HCO3 minus. So again, instead of affecting the pH, the OH minus will react with the weak acid, forming more conjugate base. So you get water out in these reactions. We could rewrite this as H3O plus so that we can specifically show the water. But you get water and a weak acid and a conjugate base instead of having acid and base just sitting there affecting the pH of this thing. Okay, so there's a visual representation of this on the next slide. You start with a weak acid and its conjugate base. And if you add strong acid to it, it will react with these guys, the A minus, and form more of the weak acid. So you use up some of the conjugate base and form weak acid. But now you just still have a weak acid equilibrium, right? You had a weak acid equilibrium here, you have a weak acid equilibrium here, because instead of this strong acid messing around with the pH, it just messed around with the concentrations of the weak acid, weak base, okay? If I had added strong acid to water, it would, drop the pH a lot. So it's preventing that from happening by converting some of the A minus into HA. On the other side, if I were to add base to just water, it's going to skyrocket the pH, okay? But when I have a buffer in there, that base reacts with the HA and converts it to A minus. So you get a little bit more A minus, a little bit of less HA, but the effect on the pH is minimal because you're not actually leaving OH in the water. You're converting it to the A minus and just making the ratios a little bit different. Okay, so when you think of buffer, think of like keeping it the same, like what other way do we use the term buffer? Like I'm thinking of a physical thing, like if you have a padding or something, right? It like minimizes the impact. Okay? All right, so there's a couple things that are important to know when we're talking about buffers, and that's, I'm gonna go back to this first slide. So the buffer will maintain the pH similar to the pKa of the weak acid. And that's not written explicitly here. Let me see if it's there. It's sort of here, so I'm going to rewrite this. So the pH of the buffer is close to the pKa of the weak acid. So like in acetic acid, the pKa of acetic acid, remember pKa is the negative log of the Ka. So the pKa of acetic acid is like 4.7. That would be a terrible pH to maintain your blood at. This would be a really bad buffer for your blood because your blood is supposed to be around 7. The pKa of carbonic acid is around 7. So that's why our body uses that buffer to maintain the pH. So you want to pick a buffer that's near the pH that you're looking for. The pKa is near the pH. Okay? And then it will generally keep the pH within 1 unit on either side. So that's what this buffer range is, approximately pKa plus or minus 1. So again, for acetic acid, I think it's 4.74 is the pKa. So if you were using this as a buffer, you'd probably maintain the pH from about 3.7 to 5.7. And then these two other things are, you want to have a lot of the weak acid and the weak base. Because like in this picture, if I only had, if I only had really small amounts, there's only so much A minus that I can use up and make HA. Or there's only so much HA I can use up and make A minus. So we want to have lots of it. We want to have high concentrations. So like the higher the better. If it's 2 molar, that's better than 1 molar. Okay? So we want the pKa to be near the pH we're looking for. We want there to be a lot of the weak acid and the conjugate base. And then the third thing is we want them to be in close amounts to each other. So like when the middle one, I have them drawn as equal, that would be ideal, is if there was 1 molar and 1 molar, or 2 molar and 2 molar. You don't really want it to be like 2 molar and 1 molar, or even worse, like 2 molar and 0.5 or something, because then you won't have enough of one or the other to buffer in either direction. Because buffers are not just for if an acid gets added in, you want to also be able to add a base. So you want them in equal quantities and you want a lot of them. Okay, so that's these 3 points here. You want more, lots of them, higher concentrations, and you want similar amounts. And then what's really nice about these is that, and I think I did this in my other class and I think I'm going to skip it in here, is that you don't have to use ice tables here, okay? We will always, I will always give you acids that have Ks that are small enough that you don't have to, you can ignore like the minus X and plus X, which means that we can use a simplified version of the ice table, and instead of actually doing the ice table, this equation was developed. It's called the Henderson-Hasselbalch equation. And it comes from the ice table, comes from the simplified ice table. If you care, feel free and I'll show you how it's derived, but it took me like 5 to 7 minutes to do it in the other class, and it was like, I think it would be better to just do more practice problems, okay? So this substitutes in for the ice table for these problems. Okay, so let's jump in and do an example of this. So it says a buffer contains 0.25 molar of the HA, the weak acid, and 0.2 molar of the conjugate base. Okay? And then it says calculate the pH of this system. Gives you the Ka. So this is pretty good. They're in relatively close concentrations. They're not super high, but they're relatively close. And if you remember, I think I said the pKa for this was somewhere around 4.7. I want you to calculate it so that you double check the actual number. But it's around 4.7. So this will keep whatever solution this is in, this will keep the pH near 4.7, even if I add a little bit of acid or a little bit of base, okay? We're not talking about adding the acid or base yet. We're just talking about what's the pH of the buffer before I do anything to it. So we're going to use that Henderson-Hasselbalch equation, pH equals pKa plus the log of A minus, the conjugate base, over HA. All right, so go ahead and solve that out. Figure out what the pH of this buffer solution would be before we do anything to it. So I'm going to write the details of the math you're plugging in here. Okay, so remember pKa means take the negative log of the Ka, so that's why we plug this in here. And then we're plugging in the concentrations. Make sure you're clear on which is the acid and which is the base. It might just be good to write like HA over the weak acid and A minus over the conjugate base like that. Okay, so we make up this buffer. It's got an initial concentration of 4.65. So what we're going to do, I'm actually going to save this for later. This is like a more complicated version application of what we just did, but I want to keep the momentum going here because we're going to take this buffer and we're going to add an acid to it. Okay? So it starts out as 4.65. So I want you to scroll down to this slide and also to this problem here. Okay? So we're going to read this problem because this is starting with pretty much the same solution. I should have left them the exact same concentrations. Oh well. Pretty much the same solution, but they're equal concentrations. So I think the original pH here is 4.74 because they're equal amounts, the pH would just be equal to the pKa. But I just want to make note of that so we can see how it changes. Okay, so I've got this thing and it says I add 0.005 moles of HCl. Okay, so I'm adding a strong acid to this buffer and it wants me to calculate the new pH. So there's going to be 3 steps that we're going to go through when we do problems like this. So if we're just calculating the pH of a buffer, we just use the Henderson-Hasselbalch equation. Okay? In this instance, we're adding a strong acid, and this would apply if you're adding a strong base too. We're adding that to the buffer, so it is going to shift the pH slightly down in the case of an acid, but not dramatically the way it would if we added a strong acid to just water. Okay? So there are 3 steps here. I talk about them as the dilution step. The other way you can think about this is finding out the initial amounts. In fact, let's say initial molarities. And then the second step is going to be what I call the consumption step, which is where we consume or use up all of the strong acid or all of the strong base. And then the last step is going to be the equilibrium step. And like I just said, we're not going to use the ice table. We're only going to have the Henderson-Hasselbalch equation there. And this 3-step process, we're going to use it when we do titrations. So we're only doing 2 topics in this chapter. We're doing buffers and titrations. And the way you approach a titration is really similar to this. So it's important to get comfortable with these steps because you're going to use them in all of chapter 18, which that's all this week is 3 days of these 2 topics. Okay, so let's go ahead and approach this for this problem. So we need to first find out the initial molarities. Well, it says we add 0.005 moles of HCl to 250 mils. So to find the molarity, moles over liters, right? So HCl, the molarity of HCl is going to be equal to 0.0050 moles over 0.250 liters, okay? Or .02 molar for the HCl. And then they actually gave us the molarity already for these 2 guys. Now, sometimes you might be mixing 2 volumes. So the third practice problem on here, which we may not get to today, it's still early, we'll see. But this third problem here has 10 mils and you're adding it to 100 mils. So when you have two volumes, that's when you have to use the dilution equation to calculate new molarities for everything. Because molarity changes if you change the volume, right? If you have a 1 molar solution and a liter of it, and then you add another liter of something, that now becomes a half a molar because it's moles over liters. So it gets diluted and changes the molarity. So when you're adding two volumes, you're going to have to do this equation. Here, it looks like it was, it's not a solid because it's HCl, but it came with just the moles. Usually they do this by like bubbling hydrogen and chlorine into a solution, okay? So you just had the moles, so you just needed to know how much the molarity of HCl was. The others don't change because you're not adding a volume of anything. Okay, so that's our first step. This is step 1. Let me do that in blue so it's clear. Okay, so we found the new molarities of everything. If you want to write down the other two, that's fine as well. So like the molarity of the HA, the CH3COOH, that's 0.250. And the molarity of the A minus, 0.250. Okay, so this is step 1. Step 2 is going to be what I call the consumption step. And we're going to take whatever we added, acid or base, we're going to write them in just like their simplified form. So either H plus or OH minus. And then that's going to react with either the acid or the base, whichever is opposite it, right? So this is just like we did in this equation here. So when we had the acid, we reacted it with the conjugate base. When we had the base, we reacted it with the original weak acid. So in this instance, since we're doing H plus or an acid, we're going to react it. Sorry, let me write that in red. We're going to react it with the conjugate base or A minus. So you could write this as A minus or you could write it as the actual conjugate base. And then what do those do? Because it's a strong acid, it reacts completely, just one second, and makes the weak acid CH3COOH. Yeah, go ahead.
How do you know if it's the acid or the base?
Perfect,
Sorry.
yeah. Oh, sorry. Like, how do you know this one is the base?
No.
Or here?
Yeah.
Yeah, because you're adding HCl. So HCl is a strong acid. And so I'll either tell you, like, you add this much acid or you add this much base, or I'll make sure it's a strong acid or a strong base. And those are like the 6 that are listed on the exam equation sheet. Yeah, good question. I thought you were asking about the weak ones. And those, like if it's something you're unfamiliar with, just remember they'll always differ by an H plus. So whichever one has the extra hydrogen, that's your weak acid, and the one with less hydrogen, that's your conjugate base. With this guy, it's something you've seen a lot before. I think there was a problem though that was a little bit less familiar. Okay, so in this one, because it's a strong acid, it is not an equilibrium. The arrow should go all the way to products. And that's why I call this a consumption step, because you're going to consume all of the strong acid or all of the strong base. You're not doing a change like a minus X. If you remember, we did this when we talked about how a strong acid reacts. We're going to use up all of the strong acid. So I'm going to write down what those amounts were under each one, just like I was doing an ice table. And I'm actually going to think of it, if this is helpful, I say ICF. So now instead of change, I'm going to think of it as initial, consume, and then final. because it's not an equilibrium, and the change, it's not an unknown change. We're consuming all of that acid. Okay, so I'm going to write down each of these starting values. And then I'm going to consume all of that acid, meaning use it all up. So I'm going to say minus 0.02 and minus that same value everywhere. This is just like stoichiometry. If I say minus 0.02, this is also minus 0.02, and this is plus 0.02. Low battery. I didn't realize that. So just have to turn this down. Okay. So minus, plus, just like I was doing minus x plus x, but I know the value here because I'm going to use up all of this strong acid. Okay, so there's going to be 0 of this, 0.23 of this, and 0.27 of that. Again, this is why it doesn't affect the pH significantly, at least, because I don't leave behind any acid or base. I just convert some of the A minus into HA. So now the ratio of the two is a little bit different. So that will affect the pH like slightly, but not in a really, really big way, the way it would if I'd added strong acid to just something, water. Okay? Okay, so now the third step is the equilibrium step, where I'm going to use that Henderson-Hasselbalch equation. So pH equals pKa plus the log of A minus over HA. These are concentrations. Okay, so go ahead and plug that in and find the pH here. So this is exactly the same as we did before. It's just now we've got different ratios, okay? Before it was like 0.25 and 0.2, I think. So we've got slightly different ratios now. Okay, so I'm getting the pH is 4.68. pKa, negative log of 1.8 times 10 to the negative fifth, because that's the Ka, and then the log of A minus 0.23 over HA 0.27. Okay, this is going way smoother than class 1. All right, so second problem, I'm gonna let you guys work these 3 steps a little bit more independently. We're gonna now add a base to this. Let's actually look, how did the pH change? Okay, the original pH was 4.74, so it only dropped by what, 0.06? So like we added strong acid and it dropped by 0.06. That's crazy. If I had added that amount of acid to just water, the pH would be 1.7. Okay? So even it would go from neutral to 1.7. This only changed the pH by 0.06. So this is the whole idea of a buffer, is it changes the pH ever so slightly. Okay, so now I want you to do the same thing. In fact, I'm gonna leave this up so that you can see the 3 steps, but I want you to work this problem. So now you're adding base, which means that you wanna react the base with the weak acid now, not with the conjugate base, and do the same thing. Okay, so do each of those 3 steps, but now with a base. Okay, so I'm gonna start the work below. So you won't see step 1, 2, and 3 right now. Or at least I'll try to not cover all of them up. Okay. Okay, so I've kind of given you the initial outline, and it should look really similar to the last one. It's just that now, because it's a base, you're reacting it with the weak acid. And it's fine if you want to write it as HA or if you want to write it as CH3COOH and CH3COO minus. Okay, so go ahead and finish that off and determine the pH here. Okay, so finishing this off, like I said, it behaves almost identical to the one above. The main difference is that your ratio is now flipped. So now when you plug it into step 3, I'm going to write this in for this one. You're going to have 0.27 over 0.23 rather than 0.23 over 0.27. Okay? So I get for this 4.81. Okay, so we started at 4.74. This was our original buffer solution. We calculated that by just doing Henderson-Hasselbalch. That was like just the equilibrium of those two things. Then we added acid and it dropped 0.06. We added base and it increased by 0.05. I feel like the rounding must have been off there. So very slight changes with adding an acid or a base. It does go down with an acid and up with a base. It's just a very small change. Okay? So I think instead of going back and doing that other problem, I think we should just go ahead and do one more of these. Also because this one's slightly different because you're diluting it. And I hope it's a different buffer. Yes, good. Okay, so same 3 steps, but now we're going to have to do that. Maybe we'll do the dilution step together. Or at least I'll get it started for you. Okay. Everyone's okay with this problem? You don't want me to stop here or anything? Questions? This is like most of the stuff we do. The first time you see it, you're like, this is horrible. It's crazy. How am I going to ever do this? You got to do more practice. The more practice you do, the more comfortable it's going to get. And it's all we're going to do this week is these types of problems. Okay, so step 1 here with this one is we need to do a dilution. We have to actually do M1V1 equals M2V2 because we're adding 2 volumes together. Okay, so the V2 in this case is 110 mils or 0.11 liters. Okay, so that should be the new volume for all of your things. So HCl, HClO, which is your HA, and ClO minus, which is your A minus. Okay, you're going to do the M1V1 equals M2V2 for each one of these. So for H2L, or HCl, sorry, it starts as 0.2 molar times 10 mils or 0.01 liters. Now, technically you can leave these in milliliters because they're going to cancel out anyways and leave you with a molarity. So it's your call if you want to change them up or not. And then that's going to equal whatever your new molarity is. That's what we're trying to find times the new volume. Okay? So you need to find that new molarity, and then you need to do the same thing for each one of these. Start with its original molarity, its original volume, and calculate the new molarity based on that 110 mils. Okay, so take a couple minutes, do each of those. I'll do them up here so you can double check them before you move on to steps 2 and 3. Okay, so this is step 1. 110, yeah, because it's 100 mixed with 10. Yeah. It might be easier to just leave them in mils just to make sure you don't make any, whatever. It's just more consistent with what we did above to convert it. But you could write each one of these. Oh, yeah. You could write this as 10, this is 100, this is 100, and then each of these is 110. It would still work out the same way. Okay, so I've got your new molarities on the side here. So it's really important because you don't want to say it's 0.2. It's not 0.2. It's only 10 mils of 0.2. So it's a very small amount of HCl that you're actually adding in compared to the other ones. So you've got to change those molarities or else it's going to throw everything off. Okay, so I'll go ahead and start working step 2 up here. Feel free to interrupt if you're not sure what I was doing with that dilution thing. So consumption step, I've written that up there. I would check after each step before you move on, just so you're not using the wrong numbers. Okay, so pretty involved calculation, obviously. Just trying to think. No, never mind. Let me just let you look at it, and everyone's going to be at different spots, and feel free to ask questions as you're going through it. I think the biggest thing is just practicing it. Like I said, we're going to use variations on this all week, but it would be good for you to practice them independently beforehand. So this is actually the extent of buffer questions themselves. So if you want to get started on the homework, which I would suggest that's a good idea, just skip anything that talks about titrations and only do the ones that talk about buffers. Okay? And that'll give you some good practice before you come in on Wednesday. All right. I'll leave this up for another minute, but you guys can go. I'll see you then. Colton, you want to take a picture of this or anything before I unplug it?
I did. I actually need to take a picture of another thing.
Oh, okay. Yeah, here. Why don't
5
I?
minutes late for that first part.
That's okay.
Yeah.
I'll let you go ahead and scroll. I'll pack my stuff up, whichever one it was.
Yeah, it was just this one.
I mean, the stuff you missed was pretty much just like the background of what a buffer is. So probably easiest is to just like, now that
Yeah.
you've done some calculations. I mean, I recorded it too, but I was gonna say you can go back and look at like the introductory videos. But I did record this. I'll
I
put
see.
it on YouTube so you can check it there too.
What was the thing about this being original 4.74? Did that have anything to do with this or
No, we didn't. So when we did this calculation, it was similar to this one, but the ratios were 0.25 and 0.25. So I just redid the calculation for us, just so you could see, like, it increased one direction and decreased the
Yeah,
other.
because I'm wondering why it wasn't used as that.
Yeah, because those weren't the actual amounts. I should have just changed it so that they were, but
Okay.
then I want to throw everybody off.
Yeah. So, I guess these are different amounts then.
Yeah,
Or-
those were 0.2, and then the one later on was 0.25 and 0.25.
Okay.
Yeah, that's why it was different.
Yeah. Well, I mean, I guess hypothetically.